All right, here we go. So, first lecture of elementary organic and biochem. Today we're going to talk about intermolecular forces, which if you took Gen Chem, you are familiar with this, and if you did not take the general chem sequence, then we probably should spend some time reviewing this, because it's going to be a big part of organic chemistry. It's a huge part. All right, so intermolecular forces are otherwise known as van der Waals forces. So if you see in a book or online, van der Waals forces, okay, it's the same thing as intermolecular forces. Now, inter means between, right? If you get on the interstate, that's a series of roads that go in between states, right? Interstate. So intermolecular forces are forces of attraction that occur in between molecules. Okay? They're attractive forces in between atoms or molecules. And so it's really important that we differentiate between intermolecular forces and intramolecular forces. So if this is my atom, and here's its bond to another atom, right? This is a covalent bond. Yes, that's an intramolecular. Okay, that's between two nuclei. Now, if there's another atom nearby bonded to another atom, and they have a bond, but these two atoms, but these two molecules just happen to be attracted to each other, that is an IMF, right? Intermolecular. You see the difference between intramolecular and intermolecular? Okay, if this molecule is attracted to this molecule, that is an intermolecular force, and we represent that with a dotted line, okay? Because intermolecular forces are way weaker than covalent bonds, okay? It takes a lot more energy to break a covalent bond than it does to break an IMF, okay? So make sure you understand the difference between intra, right? That's between two atoms, that's a covalent bond. This is really strong, versus these two being attracted to each other. So you can think about this like a magnet. Right, when you stick a magnet to your refrigerator, right, that's not a bond. You're not creating a chemical bond, that's an attraction, right? You can think of it the same way. Man, a positive end of a magnet repels the negative end of another magnet, right? That's not anything permanent, right? That's just a positive repelling a negative, or be attracted to the negative, right? It's the same thing. And so these IMFs give us a large percentage of our properties, physical properties, okay? And they play a big role in the states of matter, too. So whether or not something's a solid or a liquid or a gas has a lot to do with the environment, okay? But the IMFs play a big role in that, too. And so when we talk about like boiling points, all of that comes back to intermolecular forces, which we're going to talk about a lot in this class. So this is a figure in the textbook. Page number is probably going to vary based on the edition that you have, but this is from your textbook, right? This is all stuff that you learned in like intro chem, physical science, right? Gases have low density, liquids have higher density, solids have higher density. That's all stuff you already know. This is not news, right? But what's new here is the IMFs. The gas phase has weak intermolecular forces. The liquid phase has moderate intermolecular forces, and the solid phase has strong intermolecular forces, right? Because those are holding them together. If you're in a solid, regular, repeating arrangement, you're going to be experiencing a high degree of intermolecular forces, right? That's energy that you have to overcome to, say, melt that solid. And then you have to overcome those IMFs to vaporize that liquid to get it to the gas phase. All right, so here are pictures of water in its three states, right? And again, varies based on substance. Each substance is going to have unique intermolecular forces. That's why each substance has its unique boiling point. Okay, so like I just said, they are not chemical bonds. They are not covalent chemical bonds, okay? We take way more energy to break a bond than we do to overcome an intermolecular force. So when we talk about boiling, okay, if I take my water and I boil it, right? Am I actually breaking the bonds between the hydrogen and the oxygens? No, I'm not, right? Because if I were breaking bonds, that wouldn't be a physical change. That'd be a chemical change. I'm not breaking bonds. I am overcoming those IMFs, though. Okay, these are just attractions. So it's like flirting versus being married, right? When you're flirting, or, you know, I guess it could affect your marriage, but if you're flirting, that's not permanent, right? But if you're married, that's permanent. It takes a lot more energy to get divorced than it does to, you know, stop flirting with someone. So there's another picture, difference between intermolecular forces versus intramolecular forces, right? This would be, you know, takes a lot of money to get divorced. It doesn't take very much money, I guess. Never been divorced, but I would assume it doesn't take as much money to stop flirting with someone as it does to file for divorce. So these are all the different intermolecular forces. London forces, again, these page numbers will vary by the edition of the book you have. London forces, dipole-dipole forces, and hydrogen bonding. And I put the asterisk there, okay, because it's not actually a chemical bond. So don't let that name mislead you. We're going to go through all three of these today. We're going to spend a good bit of time today talking about intermolecular forces, because that's going to be a big part in physical properties and why things have the boiling point they have. Why is it high boiling point, or why is it low boiling point? So I'll give you a second to jot those down. I put London in parentheses because some books call it London dispersion. Some books just call it dispersion forces. Some books call it London forces, so it just depends on what author you're looking at. Dipole-dipole, hydrogen bonding. Now there are others, but these are the three that we're going to focus on. Okay, so London forces, we'll start with it. So this occurs in every atom. That's the definition. That, I mean, that's something you need to know. So occurs in every atom of every molecule. Okay, you need to know that. Because if I give you a molecule or an atom and I say, tell me the IMFs, every single time you need to put London forces, because that's in everything. So that should be the default setting. Your default answer needs to be London forces. And then you just need to decide if there's anything beyond London forces. Okay, so London forces is the baseline, and then you just need to pick, is there anything beyond that? Okay, so we pick any atom. Let's pick helium. Helium's a small atom, right? It's got 2 protons, 2 electrons. That's a small atom. That's not anything to get excited about. Now these electrons are moving randomly, right? They're moving randomly. And these 2 electrons are negatively charged, right? So these 2 electrons are moving randomly and independently of each other. I mean, in terms of simple probability, is it probable that at some point in time that both electrons could be on the same side of the atom for a split second? Sure, right? I mean, that's just basic probability. For a basic probability standpoint, there could be 2 electrons on the same side for that split second because they're going to be moving. So for that split second, for that 1 trillionth of a second, this part of the atom is negative. We use this sign as the Greek letter delta. It's lowercase delta. It means partial. So for that split second, the atom is actually more negative on this side than it is on this side, right? Because electrons are negative. If both negatives are hanging out right here, for that split second, it looks like this, right? Negative, we color red. That's high electron density. Blue we represent as low electron density, right? So for a second, this little atom actually looks like a magnet, right? Because a magnet, a bar magnet's got a positive end and a negative end, right? So for that split second, we're talking about just a tiny second in time, right? This looks like a little bar magnet with a negative end and a positive end. Now, of course, these electrons are going to move, right? So this is not going to be a permanent, it's not a permanent condition. It's just for a split second. But let's pretend that atom number 2 was nearby and its configuration was slightly different, right? Then those 2 could be attracted to each other. Now those are 2 atoms that you would not otherwise expect to be attracted to each other, right? But for that split second, those 2 atoms that otherwise would never in 100 years be attracted to each other are. And that's what's behind London forces. Okay, London forces are based on the random instantaneous attractions. We call it an instantaneous dipole. Instantaneous attractions, which we otherwise known as instantaneous dipole, because dipole means positive end and a negative end, right? So if you have a positive end and a negative end, just like a bar magnet, you're a dipole. Okay, so these are instantaneous dipoles, and they're caused by the movement of electrons, and every single atom in every single compound will have London forces. Does this make sense? They're fleeting, right? They're just for split seconds. Now, London forces can be extremely weak. For instance, in helium, the London forces are going to be really, really weak because there are only 2 electrons to play with, right? But let's pick a bigger atom. Let's pick uranium. Uranium's got 92 electrons. Would it have higher probability of this? Sure, right? Because you've got more electrons, right? As you increase the number of electrons, you increase the probability of having these instantaneous dipoles. And the word we use to describe that is called polarizability. Polarizability, right? As you increase number of electrons, you increase the probability of instantaneous dipoles, right? So the more electrons you have, the greater the probability it is that this happens. Now let's pretend that we are a multi-electron system. Let's pretend that we are a molecule. I think I've got some pictures in here. Yes, I do. All right, so now if we're looking at molecules, it's going to be even greater probability, right? Because now if you've got multiple atoms, right, we're increasing the polarizability even more. So let's, I'm actually going to skip this for a second. I'm going to draw it out because I think you'll benefit more from seeing me draw it out than looking at the slide. Now, if you think back to intro chem, do you remember when we talked about electronegativity, right? How good an atom is at sharing? Something you need to know is that electronegativity of carbon is equal to that of hydrogen. Okay, so in other words, in a carbon-hydrogen bond, electrons are shared evenly. That's importantly. That's very important. And obviously, in a carbon-carbon bond, those electrons will be shared evenly too. You're not going to share electrons unevenly with yourself. That's important because electronegativity and where electrons are hanging out is going to have a big role in intermolecular forces. So let's just start with a linear molecule. Let's just pick a 5-carbon chain. Okay. That's a 5-carbon chain. That's pentane. C5H12. Okay, so we've got a 5-carbon chain, pentane. Now let's pretend that there's another one underneath. And I'm not going to draw the hydrogens this time because I'm lazy. You can just fill it in with your imagination. Okay, the probability if these two are near each other, you can have instantaneous dipoles here, and here, and here, here, and here, 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 right? If these are in close proximity to each other, right, you have a lot of opportunity for those instantaneous dipoles. So who would have the greater polarizability? Uranium with its 92 electrons or pentane? Well, pentane obviously, right? Because you got way more electrons that you're dealing with here, right? So the trend is that if you are a linear molecule, is going to have a higher boiling point than branched molecule. Let's look at a branched molecule. We'll also use that same formula, C5H12, but it's going to be put together a little bit differently. So now this one is in a T shape. You'll learn how to name this very soon. Okay, right, this one's a T shape. This is also C5H12. H12. And we'll learn how to name this next week. Actually, maybe even at the end of this week. Now, if one of its colleagues is in close proximity, branch, 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 you don't have that much opportunity for those instantaneous dipoles, right? You've got a lot less instantaneous dipole going on, right? Because they're not as in close proximity. You still have instantaneous dipoles, but they're significantly weaker, right? So if we could draw this like a linear, right? This stacks on top of each other, nice and neat. So you can have instantaneous dipoles all throughout this thing, right? Versus this T shape, these aren't going to stack on top of each other as pretty, right? You're not going to have as much opportunity for that instantaneous dipole. So do you see how the shape plays a role in the instantaneous dipole, right? If they can stack on top of each other nice and neat, this is like pulling apart strips of Velcro, right? They're just piled on top of each other. Whereas this, they're only going to be attracted when they're close enough to be in proximity to each other, right? So the trend is that linear is going to have a higher boiling point than branched, right? If they're both the same size, right? They're both the same size. If this is 2 carbons long and this one's 5, well, that's not comparable. These are both 5 carbon chains. They both have the formula C5H12, so we can directly compare them because the only difference here is structure. Okay? If they're the same size, you can generally state that the linear one's going to be much higher boiling point than the branched, assuming that there are no substitutions going on. Right? If we took off one of those hydrogens and replaced it with an OH, that's a different story. So assuming there are no substitutions going on, everybody's just a regular old alkane. Linear molecules are going to have much higher boiling points than branched ones because they're much more polarizable. They're in greater proximity to each other, and those instantaneous dipoles can occur much more readily because they can physically be in each other's space. And so that's why I wanted to show you drawings before you see it in pictures, right? Because this is a space filling model. This is what it looks like in 3-dimensional space. Okay? Of that same image, right? So these are 2 linear molecules versus these are 2 branched molecules. More touching, greater probability of those instantaneous dipoles. Does this make sense? Okay. And this is what I just said. Longer the chain, the stronger the London forces. So if we're comparing a 10 carbon chain versus a 30 carbon chain, right? The 30 carbon chain is going to have way stronger IMFs. The 30 carbon chain is going to be a solid at room temperature, whereas the 10 carbon chain will be a liquid. Okay? And again, we can only compare if they're similar size, right? If I give you a branched 20 carbon chain and a linear 3 carbon chain, that's not comparable, right? They need to be similar in size. So here's some data. These are all alkanes, which we'll get to on Wednesday. Learning the formulas for alkanes is not difficult. It sounds scary, but it's really not that difficult. Right, these guys are all gases at room temperature. 1 carbon, 2 carbon, 3 carbon, 4. These are all gases at room temperature. These ones in purple are all liquids at room temperature, and then these guys are all solids at room temperature. All right, so a polar molecule, that's the end of what we're going to talk about with London forces. Now I'll move on to dipole. So any polar molecule is called a dipole. Di, referring to 2, and pole, right, like a positive in and a negative in. So if you think about a bar magnet, right, that's a dipole. It's got a positive in and a negative in. If you have a polar molecule, you got the same thing going on. You have a positive in and a negative in. We use this Greek letter delta, that's lowercase delta. Uppercase delta looks like a triangle. So this is lowercase delta. That's partial positive. This is partial negative. Right? Fluorine's the most electronegative element. That's why this end is negative and this end's positive. Water's also polar, right? We talked about water in intro chem, I know. Water's got 2 lone pairs of electrons on the oxygen atom. And oxygen's way more electronegative than hydrogen is. So a polar molecule has a positive end and a negative end. That's what it means. Okay, it's got poles. And so Dipole just means two poles. Now, when you put a positive end of a magnet near a negative end, what happens? They stick to each other, right? And so we can think of dipoles as just little tiny magnets. That's how they behave. They just behave like little tiny magnets. So any polar molecule, doesn't matter what polar molecule it is, any polar molecule is going to have dipole-dipole forces. So you just need to ask yourself, if I give you a molecule and say, what are the IMFs? First of all, your first default answer is London, right? Everybody's got London forces. Doesn't matter if it's a single atom or a giant molecule. Everybody's got London forces, right? So first question to ask, is it a molecule or is it an atom? If the answer is yes, it's got London forces. Second thing, ask yourself, okay, does it have anything beyond London forces? Okay, to determine that, you just need to decide if it's a polar molecule. So if it's a polar molecule, that means there are regions where there's a positive end and a negative end. Okay, regions that there are positive ends and negative ends. So if you can identify an area where there's high electron density and low electron density, that gives you a positive end and a negative end, meaning it's a dipole. So every dipole will experience dipole-dipole forces. Okay, so any polar molecule will have dipole-dipole. Now there are some specific functional groups that I want to talk about right now that are specific for dipole-dipole. So this is going to be a big player this semester. It's called a carbonyl. It's a C double bonded to an O. There are two lone pairs there. Okay. So this is just whatever the rest of the molecule is. This is whatever the rest of the molecule is. Okay, this is called a carbonyl. And it is capable of dipole-dipole. Okay, because this part right here is partial negative, this part right here is partial positive. Okay, so for instance, if I gave you this molecule, which you'll learn how to name later on, let's just abbreviate it. And I said, all right, what IMFs are in this? Your first answer is London, right? Because everything has London forces. London dispersion, or just dispersion, or however you want to put it together. And then you would also have dipole-dipole. Now, is the entire molecule capable of dipole-dipole? No, just this piece right here, right? The dipole-dipole is coming from the carbonyl. Okay, this and this, they're not capable of dipole-dipole because a carbon-hydrogen bond is nonpolar, right? You can't share electrons unevenly if your electronegativities are the same. So this part and this part, that's nonpolar, right? These pieces are nonpolar. This part's nonpolar as well. But this part right here, that's your partial negative, and that's your partial positive, and that's the part that's capable of dipole-dipole. Okay? So sometimes the entire molecule is polar, sometimes only a certain portion of the molecule is polar. So carbonyl is one we need to stick in our memory bank. We're going to look at carbonyls a lot this semester, and we'll learn how to name molecules that have carbonyls as part of the structure. So, dipole-dipole. All right, so if we look at just some data here, F2 versus HF, right? Why is the boiling point so different? Well, let's think about it. Fluorine, can it share unevenly with itself? No, right? It's nonpolar. Anybody who's nonpolar is going to have London forces only. But fluorine's the most electronegative element, right? And so hydrogen-fluorine bond is extremely polar. It's actually the next level. It's not London forces. It's not dipole-dipole. It's actually hydrogen bonding. So here's hydrogen bonding. Leads us to the next one. All right. Now, again, I put that asterisk next to it because this is not a covalent bond. All right, these are not chemical bonds we're talking about. When we say hydrogen bonding, that's just the name of the IMF, which is unfortunate and it confuses students all the time. But hydrogen bonding is not a chemical bond. Just remember, we represent a covalent bond as a solid line, whereas we represent an IMF as a dashed line. Okay, so this little dashed line, this is the IMF, okay? This is the covalent bond. So the hydrogen bonding is occurring right here. So what happens here is hydrogen bonding is basically a special case of the dipole-dipole family. And when does it occur? Anytime you have hydrogen, nitrogen, hydrogen, oxygen, or hydrogen, fluorine. This is a really polar bond. Really polar bond. I shouldn't say really polar molecule because it may not necessarily be the entire molecule. Really polar bond. Okay, so any molecule that has HN, HO, or HF in it has hydrogen bonding. So again, it may not be the entire molecule. It may not be the entire molecule. In these examples, right, the entire molecule is hydrogen and oxygen. So water is capable of hydrogen bonding. It hydrogen bonds with itself. Ammonia, NH3, right? This is the whole molecule is capable of hydrogen bonding. And then ammonia could hydrogen bond with water, right? There's ammonia hydrogen bonding with water. There's water hydrogen bonding with ammonia. So sometimes, if the molecule is small enough, the entire molecule can hydrogen bond. But if we're talking about a larger molecule, sometimes it's just the particular portion. So let's give me some space to draw here. So for example, if we have this molecule, we'll learn how to name this one soon as well. And I say, okay, what intermolecular forces do we have here? What's the first one? The default answer is always London, and then we just need to decide, is there anything beyond that? Okay, is there a region where we've got a polar, a partial positive or a partial negative?
Is the middle one since it's C and O?
Here?
Yeah.
That's a CH and that's an OH. So that's my handwriting, sorry. That's an OH. This part right here is hydrogen bonding. I think that's what you're getting at, right? Yeah. So anytime you have an OH, you will have hydrogen bonding. But remember, it's only this piece. It's not the entire molecule, it's just this portion. So the hydrogen bonding would occur 1, 2, 3, 4, 5. I'm tired of drawing it out. 1, 2, 3, 4, 5. This is shorthand notation that you'll learn soon. It's a lot quicker than drawing it out. All right, the hydrogen bonding would only occur between the two OHs. It would not occur between the rest of the chain. Okay? And they need to be oriented slightly differently for that to work. But anyway, it's just between the OHs. If you had okay, this would have London, but it would also have hydrogen bonding as well. Right? This part's going to give you the hydrogen bonding. So anytime you have NH, OH, or FH bonds, that's going to give you hydrogen bonding. Okay? Does that make sense? So it's not necessarily the entire molecule, just certain pieces of it. Now here's a scenario where we can have all three. We'll see some more examples of this throughout the semester. I'm just getting lazy, so I'm using shorthand. Okay? If I said, what are the IMFs in this? Everywhere there's a point, just imagine a carbon. Okay, carbon, 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 and then its appropriate number of hydrogens. So we have London, What else do we have? We have H bonding, right? And where is it? All right, it's just right here. And then we have dipole-dipole too, right? This one has all three from the carbonyl. Okay. Now the hydrogen bonding is stronger than the dipole-dipole, but nonetheless we have all three. So one of the things that you have to do is you need to be able to break down the molecule and figure out where the areas are. Where you have hydrogen bonding versus dipole-dipole versus maybe nothing. Maybe it's nonpolar. So there's water. Water's a small molecule, so the whole thing's capable of hydrogen bonding, right? Hydrogen bond with itself. All right, I'm going to skip to some examples. Oh, well, actually, we need to see this slide too. This is what I just said, right? We have stronger, higher intermolecular forces. We have a higher boiling point. Higher boiling point, right? Because they're strongly attracted. You have to overcome that. So the stronger the IMFs, the higher the boiling point. And then in terms of solubility, we talked about this in intro chem too, right? The structures have to match, right? If the two molecules don't match, in other words, if their intermolecular forces specifically don't match, then they won't dissolve in each other. They'll form layers, right? That's why we talk about oil and water don't mix, right? Water has hydrogen bonding, whereas oil only has London forces. Those two aren't compatible, right? That's why they sit on top of each other. And so let's just go through these kind of quickly. What kind would you expect in hexane? Nonpolar molecule. That would be just London, right? Because carbon and hydrogen have the same electronegativity. So they're sharing electrons the same. So any hydrocarbon that has no modifications to it is always only going to have London forces. Because that means carbon is not sharing them unequally with hydrogen, so there's no electronegativity difference. So it's like a piece of Velcro. Now, methanol, now things have changed. We're going to have London plus what? Right, plus hydrogen bonding, good, from that OH piece. And so grease, these grease molecules, they're just long hydrocarbon chains, carbon and hydrogen only. So that's London only, right? Okay, of these three, and you can just think about it mentally, you don't have to say your answer if you don't want to. Which one would you have the highest, would expect to have the highest boiling point? Let's just go through it together. This has only got what? This is London only, right? This is London plus hydrogen bonding, and this one's London plus hydrogen bonding, right? So we know that the higher boiling point is going to be one of these two. Now we just need to pick who's going to have the higher boiling point. It is a significant difference. Who's got the longer chain? This guy, right? Remember, as we increase the chain, the only difference between these two is chain length, right? So this one's going to have a significantly higher. Ethanol has a much higher boiling point than methanol does. So the point of difference there is chain length. And so there are the structures. This molecule, carbon tetrachloride, is nonpolar, so it would be London only, right? This one, what does it have? It does have dipole-dipole. Where? Right, with the carbonyl, but does this piece have something too? This one's got all three, doesn't it? Yeah. What about this one? Dipole-dipole from the carbonyl plus London, right? And now this one's kind of tough. I throw this one in there in Gen Chem, but we don't see a whole lot of H2S in organic chem. This one has dipole-dipole because sulfur is more electronegative than hydrogen. But I wouldn't put one like that in organic because we don't deal with H2S a whole lot in this class. Unless we're talking about thiols. We'll talk about them for a few minutes, but we don't get a whole lot of depth into thiols in this class. All right, so let's just go through them real quick. Argon's a gas, lone monatomic atom, so it's only got London, right? HBr, bromine's very electronegative compared to hydrogen. So that one would be, it's not hydrogen bonding, right? Because that's not a fluorine, that's not an oxygen, that's not a nitrogen, so it's not hydrogen bonding. What's the next level below that? Dipole, dipole. Yep, that one's dipole. And it has London as well. And then this next one would be London only, right? And then this one would be hydrogen bonding in London. You see the difference between these two, right? Bromine's less electronegative than fluorine, but bromine is still more electronegative than hydrogen. So that's why this is a dipole. This is a dipole, but it's an extreme dipole. All right, I'm going to skip that one because I want to look quickly just at some organic introduction. Just a organic introduction real quick. So one of the things that you must always know is that carbon always has 4 bonds. Always 4 bonds. Okay, carbon always has 4 bonds. Now in some transition states, you know, when you're going from reactant to product and you're in some sort of transitional state, you'll have 4, less than 4, greater than 4 bonds for very short periods of time, right? This is not, we're not talking about a stable molecule if you're talking about a transition state, because that means it's only happening for a few seconds, right? As you're transitioning from a reactant to a product, yes, you'll have more than 4 bonds or less than 4. But if we're talking about a stable molecule, carbon's got 4 bonds, right? And those can come from single, double, or triple bonds. Okay? So that introduces a lot of variety just right out of the gate, because carbon can form single, double, and triple bonds with itself and with other molecules. Right? So carbon can form lots of configurations. Carbon is a really unique substance. It can form stable bonds not only with itself, but with other molecules, I mean, with other atoms. Right? And so every time you introduce a different atom into the mix, gives us new IMFs, gives us a new boiling point, gives us new reactivity, gives us all new everything. Like I just said, it can form single, double, triple bonds both with itself and with other atoms. It can be arranged linear, and they'll be very, very, very stable. It can be arranged in rings, in branches, right? It can do a lot of configurations that'll all be stable, most always stable. And then, you know, in terms of organic variety, right? I mean, just when you think about the number of, okay, when I add another carbon to that chain, that's a whole new name, that's a whole new molecule, right? So there's a lot of variety in organic molecules. And the last thing I wanted to talk about is, what do we see in organic bonding versus inorganic bonding? Because when you take general chem or intro chem, that's all inorganic. Right? When you're talking about manganese 2 chloride, right? That's transition metal and a non-metal, right? A metal and a non-metal, that's inorganic. All that stuff out the window. We're not going to talk about transition metals. We're not going to talk about any of that stuff. We're focusing on carbon compounds, right? So organic molecules share electrons. They share electrons. They're not being transferred. Many of them are insoluble in water unless they have modifications that would allow them to be soluble in water, right? A nonpolar molecule like hexane won't dissolve in water unless you make a modification and add an OH group, and it will dissolve. But inorganic compounds, on the other hand, a lot of them are soluble in water, right? Anion, cation, that's a positive, negative. Hey, that dissolves great in water because water is positive, negative. So all the things that we learned in Gen Chem / Intro Chem are totally different from what we're going to be looking at here. So we're not going to be dealing with any of those transition metals. We're not going to be dealing with cations and anions and all that stuff. All right, so I think that's really all I wanted to get through today. Let's just stick this in here real quick. Well, no, actually, I'll put it at the beginning of next time. All right, so that's where we'll stop for today.